Hello, hello, and welcome back. We have been learning all different ways to take derivatives. And now, we're going to learn how to apply that new skill. Today, we're going to start by simply learning how to translate derivative speak into English. In our last two units, we have defined the derivative as a slope of the tangent line and the instantaneous rate of change at a point. In this lesson, we want to interpret the meaning of the derivative as it relates to the context of real-world problems. First, let's talk a bit about higher-order derivatives. If you take the derivative of a function, that's the first derivative. And you could call it y prime or f prime of x or dy dx or the derivative in terms of x of f of x. All those mean the same thing. If you take the derivative of the first derivative, you get the second derivative, and then it's y double prime, f double prime. The second derivative, let me clean this up. If you take the derivative of the second derivative, you get the third, and you can just keep going. Is there a purpose to these higher order derivatives? Well, of course there is. One example of a use of higher order derivatives is what we call straight line motion. Just an object moving in a straight line. And if you just have a function of, no derivative, just the function itself, we call that s of t, or the position function. Now we're going to talk a lot about the position function more in the next lesson, but this is a good way just to see what derivatives are doing. Now, if you take the position function, take the first derivative of it, you get s prime of t, which equals v of t. That is the velocity of that object that's moving. Then, if you take the derivative of the first derivative, you get the second derivative, s double prime of t, which is v prime of t, the first derivative of velocity, which is acceleration, a of t. So again, we'll work a lot with that in the next lesson, but I want you to kind of see what it looks like. Suppose that s of t, that's the position function, gives the distance in feet of an object from a fixed point as a function of time, t in seconds. What would be the English term for ds dt? We would call that velocity. Describe the following notation in English. What is ds dt at t equals 4? That's the velocity or instant rate of change in feet per second of an object at 4 seconds. How could you write s prime of 4 equals 18 in English? Well, perhaps at t equals 4 seconds, the object has a velocity of 18 feet per second. So let's try this out in example 2. During the Apollo 15 mission, Commander David Scott conducted the famous hammer and feather experiment to demonstrate Galileo's principles. Let's say that before this demonstration, he used his geology hammer to strike a rock, sending it across the lunar surface. Given that the moon's gravity is approximately 1/6 of Earth's, it's about 1.62 meters per second squared, and the rock has an initial velocity of 5 meters per second at a 45-degree angle upward, the height of the rock can be modeled by this position function, 3.5t minus 0.81t squared meters, where t is time in seconds. Wow, that's a lot of information. If you've never heard of the hammer and feather experiment, though, you should look it up. Very interesting. Part A, find the velocity and acceleration functions of the moon rock. Okay, so the position function we saw here. So to find the velocity function, we just take the first derivative. So that would be 3.5 minus 1.62t meters per second. Make sure you label it. And then the acceleration function would be the derivative of the velocity function. So negative 1.62 meters per second squared, which is what they told us in the beginning. Part B, how long will it take for the rock to reach a maximum height, and how high did it go? Well, imagine he hits the rock, it goes up, and then it comes back down again. Well, right at the top here, that would be its maximum height. Well, right there, we actually have a velocity of 0 because it's going up, 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 up. And then right here, it kind of stops for this tiny, tiny, tiny split second and then starts to go back down again. So to figure out when that time is, we're going to take the velocity function and set it equal to 0. And then we can solve for t. So t equals 2.16 seconds. And then how high did it go? Well, we can take that 2.16 seconds and plug it into our position function, and it went 3.78 meters high. An original function, y equals f of t, shows how quantities change with time. The derivative, f prime of t, represents the rate of change at any given moment. Real-world applications can include things like temperature changes, battery discharge, social media engagement, population growth, financial data, all kinds of things. The efficiency of a solar panel decreases as its temperature rises above standard test conditions, about 25 degrees Celsius. For a particular model of solar panel, the power output, P of T in watts, based on the panel temperature T in degrees Celsius, is given by, so here we have what's basically a position function or parent function. P of T equals 400 minus 1.8 times the quantity T minus 25. Okay, this formula is valid for temperatures between 25 degrees Celsius and 85 degrees Celsius. Find P prime of 40 and explain its physical meaning in terms of solar panel performance. All right, so they're asking us for a derivative. We have our original function, and to make taking the derivative easier, let's distribute that 1.8 through and then combine like terms. Okay, so here we have a modified parent function, and now we can take the derivative of that, and you get P prime of t equals negative 1.8. Well, they want to know P prime of 40 and what that means. So if you plug in 40 here, well, nothing happens because there's no variable there. So basically what that's telling us is no matter what temperature between 25 and 85 degrees, the power wattage is going to remain at a constant rate. A constant rate of negative 1.8 watts per degrees Celsius. Well, what does that mean in English? When the solar temperature is 40 degrees Celsius, its power output is decreasing at a rate of 1.8 watts for every 1 degree increase in temperature. The negative value indicates that as temperature increases, well, the power output decreases. Let's try this one. The battery charge level, B of T, in percentage of an electric vehicle during highway driving is a differentiable function of time t. The table below shows the battery level recorded every 30 minutes during a long distance trip at constant highway speed. Use the data from the table to find an approximation for B prime of 90. Show the computations that lead to your answer. Okay, so we want the rate of change at 90. Well, what do we do with the table? We can't find an instantaneous rate of change, but we can find an average rate of change. So let's take something below 90, like 60, and something above 90, like 20, and we can find the slope of those 2 points. This is called the difference quotient, and we're basically just doing y minus y over x minus x. and we'll find an average rate of change because that's the best we can do right now. So we have an average rate of change of negative 0.4 percentage per minute. Example 5, a high school student posts a TikTok video at noon, t=0. There are already 1,000 initial views from the beta viewers feature. After posting, the graph shows R of t, the rate at which new people are viewing the video per hour throughout the day. Time t is measured in hours from when the video was first posted. Is the number of total accumulated views of the video increasing or decreasing between time t=2 and time t=3? What do you think? Well, although this graph is decreasing, the rate is still positive this whole time. So the total views are still increasing between time t=2 and time t=3. Although the viewing rate drops from 1,200 to 800 views per hour during this interval, it remains positive, meaning the new views are still accumulating, just more slowly. So that's a quick introduction into how we can use derivatives in real life. We'll dive more into that in some upcoming lessons. For right now, appreciate you being here, and I will see you in the next video.